It's the first time for me to give a talk at UNS. I'm very honored. And so I've been doing augmented reality for a long time, so almost 25 years. And then maybe 6 years ago, I started using generative models to kind of, because it's the future of computer graphics, I realized. So, and now in my talk today, I want to speak about this convergence of augmented reality and artificial intelligence. And you can see the acronyms is AR and AI. And actually now, very recently, so May 1st, I made a new team in Paris-Saclay, which is the team AR+AI, which is about augmented reality and AI. So I want to speak about today about this new team, but more generally, I think this upcoming research direction, which I think will be very important. Okay. So let me start with an example. So you can see it's me actually and my wife, and we are fighting. And then you see B actually is a photo. So this is the photo of the bird view of me. And now C and D are AI generated. So when you see that in C and D, maybe B in the photo, my expression is angry, and C is neutral, and D is actually I'm smiling. And you see this is really using a diffusion model, and I will explain in more detail how it works. But you see, it's not just a cheap thing that my mouth is changing, but you see my eyes and actually all muscles in the face are working, and it really makes a new face. And of course now there she's wearing glasses, so it's augmented reality glasses, so in real time we want to modify the world around us. And while you may maybe not agree with this example, because of course there are ethical constraints and the law, jurisdictional constraints and so on, I think there's a lot of power to use diffusion models for such scenarios. And then really it shows what I'm very interested in, and also now my team works on, is this combination of augmented reality, artificial intelligence, and this kind of collaboration or interaction between people. And so I want to show you that the example here I showed about making people more smiling, it's very specific, but actually it can be much more general. So, as you know now on arXiv, there are new papers coming out all the time. I think my part of my slide is occluded. I don't know how to get rid of this. Oh well.
In the recording, it will show correctly. Maybe for slides.
Okay, but this is like a recent arXiv paper. I think it's December last year. And what they show is that for diffusion models, they can learn any concept, actually. So basically, you can create something they call concept sliders, which allows you to do very fine-grained manipulation. You see the examples, okay, there's smiling, makeup, and age. And not only that, you can also combine them. So you see now they made one slider for the cookedness of food, and one for fine dining. And you can combine them. And in the paper, they show up to 50 sliders they can combine, no problem. Very small increase in computation time. And this is so interesting, because I imagine very soon, when we have nice AR glasses, then I want to train a slider on a thought-inspiring environment. And then as I walk around, I can turn this up, and then I have many great ideas. And then, so often in these kind of papers, like we learned from Quentin, right? So, people claim something and then it doesn't really work. So I think one day I did some tests. So I show you some tests I did with concept sliders. So on the left side, I'm trying the smile slider, and on the right side, the age slider. So you can see how Madonna would look like without plastic surgery. And you see that it's quite interesting because it's really quite localized. So if you look at the Will Smith, okay, some things happen to his arm, but mainly so most of the changes really happen only to the face and only to the portion which affects smile. And then also here I tried the combination. So I tried a festive slider, a beach slider, and I combined them together. And you can see it works. Then quickly, now after this teaser, what I'm going to talk about, a little about my background. So I was born and raised in Munich, so I did the PhD, up to the PhD at TU Munich in 2005. And then I left Europe and was away almost for 20 years. And I came back in 2021, actually to come to Paris-Saclay. But basically my main loop was, so these are the main stations, I had many more in between, but these are the big stations where I was leading research teams. So this was first in Australia for 4 years, then I went to Japan for 4 years, then Hong Kong for 2 years, and finally I came back to France, where I was first co-directing the Venice team, and since 1 month ago, I'm directing the RI team. And here's a quick overview of our team. So it's me and the maître de conférence, Guyenne. Then we have 2 research engineers and a bunch of students, and one of them is here. And actually another one should be here, but his Francesco, but his flight, there's some strike, I think, at the airport, so he will come, I hope, tomorrow or Wednesday. And then let me quickly explain about Guyenne. Because as I said here, well, AR around the world. Like I said, always augmented reality or AR has been my research focus. So all the teams I involved in were about augmented reality. And Guyenne is a little more general. So she's interested in XR, which also includes virtual reality, which I'm not so interested in. But her focus interesting is on collaboration. And yeah, she started, so she's from Vietnam, then she came to France, did up to PhD in France, then she went to Australia, spent a few years in Australia, and then in 2019 she came to Paris-Saclay. And later I'll show some examples of what we have done together. Okay, but so this is the kind of playing field of our team. So first I want to start just with augmented reality. Right, and now there's a lot of talk about metaverse and MR and XR and what are all these things. So I'm interested in AR because, as you saw in this motivating example, it's like, okay, people talk with each other, everything is real, and just there's a little computer graphics. Right, so it's not like we are in this total dream world and everything we see is computer graphics. No, we see the real world, and just there's a little enhancement to make our interaction with the world smoother. Now I show you some AR projects I did. So I start with my favorite. So this was 2011. We got the Best Demo Award at the main Augmented Reality conference called ISMA. And what did we do there? So you see there's a lady trying our demo, and then in this demo we set the hands on fire. So and this is how it looked like. And you can see this is a very sophisticated demo, because in real time we need to do a 3D hand reconstruction. And also we need to do a real-time fire simulation. And 2011, it was, yeah, there were not so many depth cameras, just the Kinect came out, so it was very, very challenging to make this happen in real time. And you can see this is really high fidelity, so as the fingers move, you can see the vorticity of the fire, so it's really lovely smoke simulation running in real time with like 1 million particles, so it was very, technically very challenging. And then what was very amazing for us, because we showed this at this conference, and then maybe 100 people tried it over a few days, and many people, it was very surprising for us. So they reported pain. They reported that they have pain on their hands because they can feel the fire. It's very astonishing. And then after that, we started doing some experiments. And here's just, we asked people to speak out aloud what they feel. Okay, with hindsight, this was 2013, so quite a naive experiment. But after, we've done more sophisticated experiments. So I show you one in 2021, which I did when I was in Hong Kong. And that was kind of a similar setup. So we had some participants, and then we set their hands on fire. But here we did something very interesting. So we measured the blood flow. We measured the blood flow in the arm. Because what really happens if your arm is burning, then your body will send a lot of blood there. So one is for cooling your arm, but also to send defenses, because there will be an open wound. So you need to crank up the defense system. And then you can see the plot on the bottom, and you can see there's an enormous peak, and this is when you turn on the virtual fire. So I think it's very astonishing that the virtual fire can trigger the body to send more blood. And of course, now this is a very specific example, but I think this is why I'm so interested in augmented reality, because I don't think this would happen, you see the fire on the tree, or you see, but if you look at your own body and you see your own body moving in real time and something is happening, your body will react as strongly as if it was the real thing. Okay, and then next I want to talk about this intersection of augmented reality and collaboration, because now the one example I showed you was just a single person thing. So now what about if you have many people together in an augmented reality world? And so here I can show you some taxonomy. So this is from an overview paper about collaborative augmented reality. And I don't have time to explain all the taxonomy, but for example here it's interesting because you see the time. So time is always synchronous, right? So this is what I'm interested in, the synchronous collaboration. And then the space can be co-located or could be remote. And there's artificiality, so it could be some real-world things included, some computer graphics, or some blend between the two. And then there's something I totally don't agree, because if you see in this area there's focus, and then the focus it can have environment, person, object, and workspace. And for me, environment, person, object, that makes a lot of sense. Right? So I interact with things in the real world and I add some computer graphics. But what is workspace? And I think what they are thinking there in this article is like, okay, like I don't know, Quentin and me want to work on the schedule of this workshop. Then we have some Excel sheets floating in between us and we can work on the Excel sheet. But this for me doesn't make any sense. If it's that, then it's easier we sit together and work on a computer. There's no meaning of this Excel sheet floating in the real world because there's no connection. So yes, so this still needs a lot of work, I think, on the conceptual level. And the team is just 1 month old, so forgive me. But I can see the mistakes of current taxonomies. Okay, then I want to show you some examples. So this is one I did together with Vivienne. And this was in an archaeology project, and then it's some people work in augmented reality and some in virtual reality, and then they're distributed by somebody's at an archaeological site, somebody's in an office. And then in this work, what we're looking at is there's a lot of, well, it's the real world, so you will get interrupted, right? So, and then let's say I have a phone ringing in my office, I need to pick up the phone, but well, I have an avatar in some shared world where we're working in this archaeological site, then how to deal with that? So, and there we have some idea. Basically, we introduce an agent that kind of takes over while I'm away and does some interactions. Another one, which is going to be on a submission to WIST, which is a very nice user interface conference, and that is about, so if you have people working in the same area, and they do immersive analytics together. Right, so I think in this example it's weather data, so you have very complex weather data, and then you want to have it in the same space, and because it's spatial data, it makes more sense actually here. But then how can you work together? And more specifically, how can you deal with privacy? Because there are some things I want my collaboration partner to see, but some things I don't want to see, so how do you make interaction techniques for them? So these were two more serious applications. Now also I did a lot of kind of entertainment things. So now I show you the more entertainment things. So I was a professor in Japan, and at that time I made this thing quite interesting work. So, and because in Japan they have this kind of ghosts, and these ghosts they were recorded like over 1,000 years ago already. So it's a very traditional Japanese culture. So it seems in some Hokusai painting, so the famous painter who made the big wave also. So he has depicted this kind of ghost. And then I found a temple in Kyoto, like 1,000-year-old Zen temple, and they agreed that we can make some augmented reality ghost story in their temple. So let me show you that one. So you can see it's very nice Japanese Zen temple. And you see it's multiple users, so they can walk around with HoloLenses, and then they can see the different ghosts. So there's some shoe ghosts at the entrance of the temple, where you need to take off the shoes. And this is kind of one behind ghost, so he'll explain a little what's about to happen. And then there's some location-based storytelling that can walk around the temple and experience different things. And I think it's very, very unique video, because it's this 1,000-year-old temple, I think kind of world cultural heritage. And then people can run around with HoloLenses and see ghosts embedded in the environment. That was 2016, and so after I got quite interested to do more of this kind of application. So then the next thing we did is to try to make a massive multiplayer game. So this is in Osaka. So this is a train station where more than 1 million people go through every day. But even in this train station, you could play our game. And this is, of course, very, very challenging for tracking. Because, yeah, you have daytime, nighttime, huge area, many people walking through. So, show you a little more fancy video.
We introduced Holo Royale, a large-scale, high-fidelity, multiplayer augmented reality game. Holo Royale uses the powerful AR interface.
So basically what we have to do for this is
providing accurate tracking and registration interaction.
And then we are doing also model-based tracking to track against the landmarks. And because things like the buildings and so on will be robust, so they don't change so much. So always we have to track against the buildings.
Our game works over large scales.
So I know you have probably used Overland. It was easy to use it in a room, but to use it for 1 square kilometer was quite challenging.
Navigation cues to guide players around the play area.
And then I want to show you the most recent work, which was accepted at the SIGGRAPH in America. So we show in August, we will show this demo, and we will show it on stage. So it will be live on YouTube, so please watch it. And so for that work, our motivation was to, so this is currently if you go to a concert. Yeah? So everybody has their phone, and they live stream what they see, or take a video, and it's terrible. Yeah? Look at all the people. Everybody looks at their phone. There are not two people who look at each other. Right? So this is the future of entertainment and social media. So it's terrible. So I'm thinking with augmented reality, with glasses, we can get people more also to look at each other and to interact with each other instead of just looking into their phone. And so let me show you. And this we got accepted, so I'm very proud.
For SIGGRAPH Real-Time Live 2024, we present a live real-time audio-visual performance designed to be experienced by a live audience. We then extend the experience for selected members of the audience using augmented reality to give them an entirely new perspective on the performance. A research collaboration between University of Paris-Saclay, Canon Japan, Notch, and Los Angeles-based multidisciplinary artist Brett Bolton. The performance is based on Bolton's recently produced show Phases, which made its debut at MUTEC Montreal. The performance uses a custom drum projection instrument to drive visual exploration of the states of matter. Each hit or gesture of the drumstick triggers an immediate musical and visual reaction. The performance is displayed to the audience on a large LED screen, combining the real-time rendered visuals with live camera captures of Brett as he plays. Real-time particles, gas and liquid simulations are generated in Notch and rendered via their new hybrid real-time ray tracing and rasterization renderer. An audience member will stand on stage overlooking the performer and wear a Canon Unreal M1 headset. This is relayed to the rest of the audience via a live feed.
So actually when we submitted this, then we got the feedback, and the feedback was there must be two people. Because as I mentioned in this motivating example, right, if it's just one person, it doesn't really show why we're doing that. There should be two people, and then they can see visuals around the performer, but also visuals between them. They kind of animate them to look at each other. Maybe they can dance with each other, and then the visuals will interact with their dance. So yeah, now we have more work.
This is relayed to the rest of the audience via a live feed to provide context. The addition of an AR component is driven by the desire to explore new live audience experiences, with the potential for interaction not only between the viewer and the live visual, but between multiple viewers. Traditionally, VR and AR experiences have been solitary. With this research collaboration, we wish to create a more immersive and interactive experience which brings people together using technology that's likely to become ubiquitous in future. We believe that this performance can showcase how AR can add meaningful depth and audience-driven interaction to a live performance, and are excited to submit to SIGGRAPH Real-Time Live.
Okay, so now I introduced some components, so now let's get to the meat of the matter. So now what about systems that do all of these together, AR, AI, and collaborative? So we also had an example recently, so in December, we got at SIGGRAPH Asia, we got the award for the best XR demo. You can see it's me and also David was on stage there, so we got this prize. I think very nice. And so what was this? And I think the system we showed there is a great example because it's collaborative, has AR and a lot of AI components in it. And so this is kind of the scenario we are addressing. It's this kind of virtual try-on. And there are hundreds of virtual try-ons, but what's specific in our system is that there's a collaboration. So you have a customer, and the customer wants to redesign some clothes, and then they have some kind of magic mirror so they can see themselves and the clothes. But then there's also a designer, and the designer wears AR glasses, and using these AR glasses and like hand tracking, they can modify the clothes on the body of the customer. And why it's interesting is because often also it depends how you move, right? So for example, there's this about the cuff of the shirt, and now in order to see if it is the right length, it's important that the customer can move. Or in the case of the pregnant woman, or stimulated pregnancy, of course, there is also an issue, right, because it's got an unusual body shape, and it's not easy to design for that one. And now here we don't have a fancy video, but just a rough video, but you can see on the left it's kind of the customer view, so you can see there's a cloth with physics simulation on the body, and of course everything is real time. And the right side you can see the designer's view, where they can kind of adjust the surface length, the length of the cloth. And now in this system, so how many AI components are running there? So first of all, we use skeleton tracking. Then when we have the skeleton, we use SMPL, which is a parameterized model, skinned human model. So we fit that, and that gives us the surface. And then based on the surface, we can do the cloth simulation. And then after we did the cloth simulation, now we know how the cloth should look like. But then we need to composite it correctly into the environment. And for that, we need to do background segmentation, depth estimation. And then finally, also to interact with it, we need to do hand tracking. And I think it's quite astonishing. So when I started augmented reality 25 years ago, it was much simpler. But nowadays, to make a state-of-the-art system, you can see this has 2, 4, 6 components, which are real-time deep learning systems. Okay, and now I think the final part of my talk will be now more focused on this AR and AI part, so more on the algorithmic side of things. So first, let me start with something to show you kind of, because where I'm coming from is augmented reality, everything must be real time. So everything must be, 50 milliseconds per frame, yeah, or less, 30 milliseconds per frame. And that is traditionally not what AI or deep learning, machine learning is known for, because it's rather slow, right? But now it's becoming really possible to do things in real time at extreme quality. So first I want to start to show you the extreme quality. You can see these sampling, but of course not really. You can see the quality is very bad. And this is how it's made, yeah? So you can see on the bottom is the world champion breakdance guy, and then I'm on the top. And basically using some control nets, you can see every finger, every wrinkle of the cloth, everything is transferred. And it's using many things together. I also segment anything model, Prometa research, and LoRa, so custom model that's trained on me, so that it turns faces into me. And yeah, you can see the quality is extreme. But as I showed here, the render time is also extreme. So you can see, so this is like a 5-minute movie, and then it took 50 hours rendering time on an NVIDIA A100. And I think now with hindsight, it was 3 months ago, so now already many new things came out, and also I didn't do it properly, so I think it could have been done in 5 hours. But still, it's 5-hour rendering time for 5 minutes, so it's like 1,000 times too slow. But the quality is there. And now, on the other end of the spectrum, so recently we had a visit from NVIDIA, and then we wanted to show some fancy things for them. So one thing we showed them is this, so that we can run diffusion models at 150 frames per second. And you see, the quality is not so bad, so it's Elon Musk. And if I go to some random image, it clearly looks like Elon Musk. And okay, there are some problems with the eyes, and It's not very good, but well, so it's possible to make things at 150 frames per second with diffusion models. And this is running on a desktop machine, so it's not an H100 or like a data center GPU. And then also we showed them this demo, which also we brought, so you can try later, I guess in the afternoon. And that is where we can turn anybody in real time into Jensen Huang. And you see, we are still struggling, so it's still blurry and the quality is not very good. But I think it's very noticeable that it's Jensen Huang. Yeah, because also there's the traditional leather jacket, or the, the typical leather jacket of Jensen. And it was quite interesting for me because to make Elon Musk was very easy, because any diffusion model I think that exists, you write in Elon Musk, you get this photo like this, but not for Jensen. And why is that? I think the reason is that Jensen is a much more private guy, so the only photos you find from him are on the stage when he's doing the NVIDIA keynote. Whereas Elon Musk, you can find, I think, too many pictures online of him in all different activities. Yes, so now what is the bigger picture here? So I showed you, I started, well, in the beginning this example, I showed you this where I'm fighting with my wife, and in that one it took 6 seconds per image. So it's about 100 times too slow. And then in the dance video I showed you, it's about 1,000 times too slow. But so this is kind of the quality that we want. But as it's augmented reality, we need to have it real time. Then I showed you this Elon Musk demo, which is 150 frames per second, but kind of bad quality and also not very controlled. It's just we can make random faces, but it's not that I could replace other people's faces. Because in that case, I need additional things. And then if I think about this video-to-video demo for Jensen, then, yeah, we use traditional things like a custom trained model, and also we use ControlNet, which allows to control the diffusion generation. Right? So you see there, I think mainly it's an edge detection, and then based on the edge detection, we can generate images which fit more the real environment. But, yeah, so now the goal is to put everything together, so that we have extreme high quality, extreme good quality, extreme controllability, and it's all in real time. So that's the mission of our team. Okay, thank you. So that's my talk. If you have questions, I'll also stay here for the next 2 days, so if you want to talk more, you can also do it later. Thank you.
Thank you for your presentation. We now take questions. Both here and on Zoom, you can unmute yourself if you want to ask a question.
A quick question about the last LoRa control net. So what does the control net do exactly? And how does it help make it more efficient?
Basically, with the control net mechanism, you can control the outputs. Because normally in a diffusion model, you have a text prompt, and the text prompt makes something, right? But then you have, for example, control nets which take skeleton. So you run something like OpenPose, it gives you the skeleton of the person. And then if you generate, the generated person will have the same posture. So it's one way, and another one is just you have an edge detector, and then you can make generations based on the edges, or on the depths, or on the, so there are dozens and dozens of different control nets already. And but in our demo we use the most simple one, which is the cutting edge detector, because this runs very, very fast. And it's enough. Yeah? If you look at here, there are some errors here, but basically, yeah, you see it's guided, so that if you compare the two, the edges are not really the same, but it's like, I don't know, 80%, I guess, of the edges are matching, so you have some control. But of course, it's, the more you control, the slower things will get, and so it's a fine balance to have it real time, but still have enough control. I think, for example, clearly what would help here is to use another control net for the pose, right? Because then you ensure that the arms are correct, right? You see, for example, here, yeah, in the input frame on the left, both arms are up, on the right hand, no. But if we add the open pose control net, then 100% the body posture will be the same, but you wouldn't have 20 frames per second as here, but maybe 10 frames per second, and then it's too slow.
So basically it checks that both edge maps are fine.
Thank you for the presentation. It was really fascinating. So I was wondering about the first thing you showed about the hands-on fire. So have you followed up that lead about the crystal flow? Have you done any follow-up on that subject? Or
yeah. So the most recent thing I did was the no, I need to reshare. Just a moment. Yeah, the most recent work was this in 2021, when we used the laser Doppler to measure the blood flow. And that was a PhD thesis. Then after that, the student also did EEG experiments. And I think the next thing, okay, and then the thesis finished, and I went to France. But so the next thing I would like to do is to do fMRI, to really understand what's happening in the brain also, because that the blood flow changes, yeah, it's all triggered by the brain.
Yeah. And have you thought about possible therapeutic uses, right?
Yes.
And doesn't it plateau, or maybe you get hyper flow at the beginning, and then
there's several problems.
Realizes that this is useless.
There are several things. One is, for example, that in these experiments, it worked for about half of the people. Half had zero effect, and half, they had these huge peaks. And then also we started doing experiments to find this out. Who are the people where it works, and who are the people where it doesn't work? And my hypothesis was that, let's say there's hypnosis, and then there are people who are very easy to hypnotize, and people where it's impossible, you can never hypnotize. And then my assumption was that the people who are easy to be hypnotized, they have this peak. The one who cannot be hypnotized, no. But then we started working with psychologists, and then it turned out an experiment for that would be very complicated, because then you need really many hundreds of subjects, and you need to make a personality test with each one, and so I'm thinking that for me it seems the next feasible is to do an fMRI experiment. And I know that on the plateau there's something called Neurospin, which apparently is a big fMRI facility. So I want to get in touch with them and continue this research. Because I mean this is a fire, right? But you could think also about cooling. Because actually the authors 2 and 3 here, this is in Hong Kong, and they are experts for burn wounds. And they were telling us that, well, they have in Shenzhen, China, which is near Hong Kong, there's some hospital for children with burn wounds. And it's always full, so there are thousands of children with terrible burn wounds. And then for them, couldn't we make a therapy system? And then there it would be more to cool. Then you maybe show virtual eyes on their arms, and then they have terrible pain, but then the eyes could cool. And there could be a cooling effect, so you have a non-medical way to mitigate the pain. And I think, of course, the sky is the limit. So now we can fire an ice, but you can think of many more things that can be done.
My question is about the concept sliders that you were showing before. And in that, I mean, usually when we talk about concepts, so do we give some sort of priors to the neural networks, or is it purely learned from the data that we have?
So the way they do it is to train the concept sliders. They basically generate many synthetic images, and then you need to kind of cluster them. So you say, okay, these are example images for, I don't know, beaches, and these are example images for not beach, and then the in between, and so that's how you train them. So, but it's basically it's an archive, it's open source, so they have also training instructions. But so far what I did is, because I think they have 20 sample sliders that they already trained, and now more and more people use that, and they train their own sliders, but I haven't yet trained my own slider, but I really want to. Because now the Jean Zay recently got H100 cards, So now I'm thinking to use the Jean Zay H100s and train the, for example, this expiring environment. I think that's really a slide I want to train.
I have one question about the AR glasses you use. So when you use glasses, is the computation done within the glass or on the cloud?
Nice. So the glasses we are using are the ones from Canon, and I think because a long time I used to work for Canon, so I left this out of my CV in the beginning. But basically, I used to work in Japan for Canon in the team that makes AR glasses. And for example, in this demo here, this is some old version, which we use. And now in the newer work, so in this one, also we are using these Canon glasses. And they are basically connected to a high-powered PC. So they kind of need a 4090 to run. So I think for me, the initial prototyping and doing evaluations and so on, I believe in this kind of local approach. Or maybe backpack computer, that you have a strong GPU and carry it on your back for some experiments. But of course, in the future, it should be running in the cloud. Especially if you do very heavy stuff that maybe a backpack computer even cannot do. Right? So if I want to make a neural radiance field of my environment, it's probably not so easy to do on a laptop. And right, and then it becomes interesting, right? Because then you have things like you can do some things. Maybe I guess the best will be some hybrid system that you do some things on device, and then maybe you get some low fidelity kind of preview, while some expensive thing runs in the cloud. So you have like two rendering loops: a local one, which is very fast but not so good, and a slower one with high quality in the cloud. And then they need to synchronize, and you need to feed the high quality results into the local system. Yeah, but I hope to work on that with you soon.
That's nice, because my main concern here would actually be if there is latency because you have to connect to the cloud. It's not a big problem, for instance, if you watch on a screen, but for instance, if you use a glass, if someone moves in front of you but you don't see it right away, it could be a bit strange.
Or... It could kill you, right? So car comes and there's a 1 minute delay.
So I was wondering if there's actually something to at least show what is happening in addition to the rendering in the meantime before it is rendered.
Yes, I think it should be one guiding principle that you modify as little as possible. And let's say if I imagine some application, I walk around in the street and then maybe I'm depressed, so I want everything to be more happy. Then look more friendly to me. I guess there must be some safety mechanisms, the cars, or like there must be a way to detect dangerous objects, and these should always be visible. You cannot, I don't know, the thief coming who wants to rob you should also be visible, but it's tricky, right? Because now if I made this example, we want everything to look friendly. If now the thief comes, he should not look friendly, right? So it's complicated. There are many, but well, that's the reason.
Do we have any other questions?
If not, then please try. I think maybe in the afternoon David will have the demo set up. Then you can try the high-speed diffusion models and also this magic mirror. And thank you.